Hello, everybody. Welcome to the Fire Science Show. Finally, got you the episode I was talking a lot about in the previous episode, and that is the glass in fire experiment. Extremely important subject in fire and fire dynamics studies, and very, very relevant for the whole fire engineering concepts of buildings. And yet, not that many people research that, and it's not very easy to find experts on modern glazing in fires. So I'm really, really happy that I found one, and that is really, really good. And that is Professor Wang Yu from USTC in China. Yu is probably better known for his involvement in the IRIS project on informal settlements, where his project won like all awards that were available to get in the last years. And that was an amazing development, and something that eventually must come into the podcast, because I would love to share that with you. Anyway, Yu has done his PhD on glass in fire. He did extensive research on glazing in fire during his time in Edinburgh. Now he's continuing that in China. So he has really great experience, experimental and modeling experience in the glass behavior. A lot to learn from him. This episode is probably more engineering and technical than the usual podcast episodes. So there's a lot of terms flying around without warning. So maybe I'll try to give you a little background on that. So we're talking about the glazing and different glazing technologies. If you think about a simple glass panel, like the simplest form of glass, that would be something we call the float glass. And that's just glass, nothing else. Now, if you subject this glass to temperature during the process of tempering and then cooled it down, you pre-stress the glass and you receive something that we call the tempered glass. And that's something that behaves completely different, as you will explain. And this is something that is very focal to his studies, because this type of glass is very force strain resistant. So it's used for facades, especially facades on large buildings. You cannot build a really big glass panel out of different types of glass than that. So it definitely is an important type of glass to be considered. There's also more. There's laminated glass. So you take a piece of glass and you put a foil on it that changes some of the properties of the whole glass system. You receive basically a float glass that sticks to a layer of foil. And then the foil changes the behavior, because suddenly if you crack the glass, pieces will not fall off because they're stick to the foil. So again, different behavior. And many times in the episode, you'll hear a name, PVB foil, that's polyvinyl butyrate or something foil. That is a key component in this laminated glass and connecting the glass layers together. And it has certain characteristics, certain properties that we need to study to understand how the glass behaves as a system. And finally, you'll learn that in the episode, but glass is really critical for compartment fire dynamics, the development of fires. We make many assumptions related to the ventilation conditions in which the fires take place, but do we really consider if these conditions can occur in our buildings? Like, it's really modeling a huge compartment fire, taking into account that 200 square meters of windows are already open when the fire starts. Is this really a realistic fire scenario? I don't know. I hope you make up your own opinion after this episode and you learn a lot about the glass behavior of fire. And I was thrilled to finally have someone to chat about this topic, because I find it one of the fundamental for modern fire safety. So yeah, it's a little longer introduction than usual. I hope the episode meets your high hopes. So yeah, let's not prolong this anymore. Let's spin the intro and jump into the episode. Welcome to the Fire Science Show. My name is Wojciech Węgrzyński, and I will be your host. Everybody, welcome to Fire Science Show. I'm today with Professor Wang Yu from State Key Fire Laboratory of the USTC from China. Hello, Yu. Great to have you on the podcast.
Hello, Magic. Yeah.
Thank you for taking my invitation. I was looking for an expert on glass or glazing in fire for a while, and eventually you get recommended. And I'm super excited to do this interview because this subject for me, with every fire experiment I make, is more and more important. So maybe let's start with a nice way. So maybe can you tell me about your previous studies on when did you build your interest on glazing in fire, and how did it develop for you?
Actually, I started these areas from my PhD study. I mean, from nearly 10 years ago. So during that stage, we conducted some experiments and also developed numerical software using the finite element method to predict the thermal stress varying and the strength during the fire or the thermal loading. And we successfully predict the crack paths and crack propagation of the glazing. And after that, so that we can make some full-scale experiments and validate our simulation. So we started this area from there. And for now, we are conducting some experiments to understand the interaction between the glass and the compartment fire.
This is exactly why I brought you here, because this interaction is very fundamental to understanding fire and fire design in buildings. First, maybe let's start with the glass, because if you look back 30, 40, 50 years ago into the golden era of fire science and experiments being conducted, the glass used in buildings 30, 40, 50 years ago was a completely different thing than what we use today in terms of its thermal properties for the buildings, but also in terms of properties to fire. Now we have this modern glaze technologies with tempered glass, laminated glass, different infill panels, different layers, 2-layered windows, 3-layered windows. Can you try and comment on how this modern technology differs from this old type, like single glass panel windows from the far past ago?
Yes, sure. It's a very good question. So actually, 30 or 40 years ago, like Pagani, they started very elegant research to study to predict the non-tempered glass breakage mechanism in fire. So they developed a good software which is called BreakOne, and they can use this software to predict the temperature in compartment and then predict the temperature difference of non-tempered glass. But that kind of glass is primarily used for the windows, not for the glass facade. So actually, in the very recent 10 years from my PhD study, we started to focus on the glass facades on the high-rise buildings. Mm-hmm. So like what you said, this is very different. For example, in China, it is required that you have to use the tempered glazing in the glass facade. So I think the most different is that the tempered glass, when you manufacture the tempered glass, actually it's manufactured from the non-tempered, from the fluted glass. And during the manufacturing, if you reduce the glass surface temperature very quickly, then you will get some pre-stress in the glazing. So namely, it has 3 layers of pre-stress, the compress, the tensile, and the compress. Mm-hmm. So due to this pre-stress, then the glass can withstand a much higher temperature than the fluid glazing. Mm-hmm. So I think this is very different. So that's why I think when we study the glass, we have to go into the stress under the fire and combine the thermal stress and the pre-stress together to get the critical point of crack initiation. Then after it's crack, different from the fluid one, for the tempered, it will totally fall out for the single glazing because they have to release the energy in the pre-stress glazing. But for fluted glass, they have a lot of crack paths. So that's totally different. So actually, why we are now studying the tempered glazing? Because for the fluted one, if we wanted it fall out in the fire, so it have to be a crack ignition, crack path, then cracks cross each other to forming the islands. Then some pressure may happen, may press on the glazing or some fire, so make it fall out.
Like a part of the glass where the island of cracks has made, and then this part will fall off, not the whole window, right?
Not the whole window. Mm-hmm. Yeah, only the islands.
Mm-hmm.
Yeah, so it may fall out gradually.
Mm-hmm.
So, for example, maybe 10%, then 50%, like that. So it's very difficult to predict that. To be honest, a lot of probabilistic problems. The fire is often complicated, and actually the glass, also, why the glass crack? Because it has a lot of very tiny flaws, which you cannot see it on eye.
Mm-hmm.
Yeah, so the tiny flaws distribute in a very random way. So both the glass crack initiation, both the fire are very probabilistic. So very difficult to predict that. But so it's a very difficult topic, to be honest. And now when we are focusing on the temporary glazing, so you have to deal with the pre-stress problem. But the good thing is that once it crack initiation, then you can assume all the wall collapse, right? You can assume a new vent is formed. So it's kind of easier than float glazing, actually. But the pre-stress is much more complicated. So it's very difficult to develop a model of this. But now we are focused on in these areas, and we recently developed a numerical model, but it's still under the validation of bio-experiments.
And do you have any experience with laminated glass? Because it is commonly used in Poland. Like they would use, I think it's float glass, but with a layer of plastic foil on one side. Can you maybe tell us more about that?
Yes, we indeed conduct experiments about the laminated glass. But for limited glass, it's much more expensive than the single one. So before research, you have to consider the expense. But if you can withstand the expense, so of course, laminated glass is a better one to give the better fire resistance. Because from our experiments, even the both glass cracks, even for the float glass, not for tempered glass, they still can still together with a PVB layer. Or some materials. Yeah, so it's very difficult to fail out for this kind of glazing. And you have to make the PVB charring and even melting, but difficult actually, so that the glass can fail out.
My experience is also that for laminated glass, I've seen like the cracks propagate through the glazing like a spider's web, but it would still stay in place. It would become soft. You could like punch it with your hand and move the glass, not break, but move it. Like make crater inside, but not break through, but it would not fall out. So in the end, you have the world in which there are literally three different mechanisms, like float glass, where you would have cracks propagate and open islands in the glass, and parts of the glass will fall out. Then you will have the glass exposed to fire from both sides. So this will quickly lead to more of the glass cracking and failing, and more and more and more. Eventually, the glass will completely fall off. You have tempered glass, which is much more resistant to heat. But once you pass the critical temperature, I don't know, some
difference.
Yeah, temperature difference, temperature gradient inside the glass. Once you pass that point, you have the cracks. You can assume the whole thing breaks out because of the release of the stress within the glass. And then you have laminated glass, which acts like floats. So you have the islands of cracks, but they don't fall off. They sticks to the foil membrane until the foil membrane is destroyed. Did I get that correctly?
Yes. I think very, very correct.
Yeah, that's really cool. And in Poland, I see this, especially laminated and tempered glass. I see them used together in projects. Like we often have, I'm in a recent projects for tall building that I had. We had 3-layered glazing. First, there was the laminated glass. Then there was some argon layer, like a part of the window filled with argon gas. Then there was a middle section which had some special foils to reflect infrared and ultraviolet light to improve the thermal properties of the inside. And then the outermost layer was tempered glass because probably of its resistance to stress and forces. So in essence, we had 3 glaze panels between the interior and the exterior. And they were also not made from like it was not a single layer of glass. The laminated one was like 3 or 4 glued together. The same in the middle, it was 2 of them glued. So in the end, you literally have multiple layers of glazing on your way out. How do you deal with that problem in your modeling? Are you modeling just one layer, or you're modeling all the layers and stresses in all of them separately?
Yeah, and actually you have to evaluate some other factors. For example, you have to know the heat transfer analysis for the laminated glazing. Yeah, you have to validate the temperature inside it, and also the ambition side of the glazing. We have done that. So I think the FEM method will do this work. And then after you get the temperature and temperature gradient, I think then you can know when the glazing can break. And after that, we have to understand more about the PVB properties. And actually, for this kind of glazing, I do not think it may fall out very easily in a normal compartment fire. Not easy, but why it can fail out? We also have done some double layer glazing or 3-layer glazing. I mean, not about PVB, but by some airspace. They fail out actually the primary caused by the frame deformation. Yeah, you have to focus on your attention to these areas. For example, we have done a full-scale buildings. I mean, we born 2 real compartments in China, my group. So actually, the glass fall out, which is caused by the PVC glass frame. PVC can even burn. In the fire. So when the structure lost its stability, so then the frame with the glass will totally fall out. I think this often happens in a real fire. Yes, but in the previous research, we did not consider the frame constraint a lot. But in Edinburgh, David and I were supervising a master student together. That student had done very good master thesis. That is about his name is Paris, from Poland. Very clever guy. So he had done the combination of the fire and also the deformation from the frame, and the impact both impact together on the glass pan. So that will give you very different breakage mechanism. Yeah. So I think for the case you mentioned, I think we can focus on more about the frame and also more about the PVB properties. Yeah.
I remember one experiment we were doing, like a full-scale experiment, and I am known for notorious sticking of my iPhone into fire experiments, trying to record. I've got my hand burned like 5 times already, and my hand is much more fragile than the iPhone is. And there was this window. We had a full compartment fire, like fully flashed over compartment fire, and there was a window frame in that room. And I really, really, really wanted to capture on a video how the glass breaks and falls off. And I was standing there like an idiot, for like good 3 or 4 minutes next to a fully flashed over compartment, waiting for this damn glass to break. And what happened was exactly what you've said. It was not the glass that would break. Like, I mean, I could see like the layers inside crack. I could hear it cracking. But on my end, on my side, on the outside, I could not see cracks. You could hear them, but you could not see them. It was like dark inside and so on. So in the end...
So is it 3-layer glazing?
It was multiple layer glazing. I don't remember how many.
Okay.
So at least 3, maybe even more, because it was for some sort of very energy efficient housing. So for these projects, you use multiple layers of glazing. It was not a skyscraper. It was just a normal window.
I know.
Eventually, the rubber gaskets have failed. The frame melted a bit, and then the whole thing slid off. And the glass was like, it was horrible. I really wanted to capture the glass breaking, and what I saw was glass falling. But that is an interesting behavior as well, because suddenly you open the whole window, not a part of the window like in the float glass scenario that was mentioned previously. So maybe we'll move to the fire side. So you've mentioned you now researched glazing failure in connection with compartment fire dynamics. Maybe you can bring up the audience in line on why would we care about glazing failures in fires? Why is it so important for the fire dynamics?
Yes, actually, it's also a good question. Actually, in a lot of previous research, when we do compartment fire, we often assume there are no glass panes in the compartment, right? We just assume a flash will already happen, the glass totally gone. But actually, in a real fire, especially in the high-rise building fire with modern tempered glazing or laminated glazing, they are there even after flashover. So you cannot simply assume they are gone. And so we have to understand how and why it fall out. Because once it fall out, the new air will enter the compartment to give more oxygen to the fuel, especially in the ventilation control stage of the compartment fire. And also, when the glass break and fall out, it gives a new path for the flame spread. It can suddenly change the flame spread direction, maybe to the facade, the high-rise building, the compartment facade. And also maybe it can give the smoke a lot of possibility to go to the other floors or the other rooms, which will cause much more death. So I think that's why this is important, because before you understand this, it's difficult to give the prediction for real fire spread in high-rise buildings or in our normal modern buildings. Yeah, so I think we have to learn these areas. Because primarily because the modern glass is so tough to break, so it may not break after flashover. So we have to know even after flashover when it may break and how it can happen. So that's why we started these areas in recent years. Primarily, especially for some high-rise buildings, the glass facade areas is a lot of glass facade areas. So once the glass fall out, the component fire may suddenly change it from ventilation control to fuel control fire. So in our previous, maybe 30 years old, maybe no problem. The windows are always small, but now people like big window room. So it can change the opening factor much more significantly. So I think we have to learn these areas.
In the very, very far past ago, you would rely on something like a standard time-temperature relation for designing your structure well, you still do, but that was the only understanding of the fully developed fire back then. Eventually, we got the compartment fire models, which connect the size of the fire with the amount of air available through opening factors, like you mentioned, the ratio of the part of the building that is open to the surface of the structure inside, in more or less. That's not an accurate description, but that's the physical meaning of it. And now, if you want to understand the temperature in your compartment, you need to know this opening factor. You need to understand how much air is available through entrainment into the compartment and how much can go outside of the compartment from the fire. And we often, when you would design a building, you would know the area of your windows or area of glazed, and you could mistakenly assume that all of it is empty, that you have the maximum possible open factor because everything fell out, which may be the case after a few hours of your fire, or an hour or 2 hours, when you have exposed this glazing for the maximum temperature for a long time. It could fall out, actually. And it could be a description of the maximum biggest fire you can have in that room. But if you have a fire that is growing, a fire that is building up and transitions to flashover, it has the whole glazing closed. Now, a good question is, are the conditions in that early stage of the fire sufficient to break the glass easily, and in what amount? Do you have any experience in like pre-flashover fires destroying glazing or opening these new flow paths, or it has to be like it must be conditions like in a fully flashover fire to destroy this modern glazing?
Yes, we have done some small-scale experiments and also done some full-scale experiments. For the small-scale experiments, when the tempered glass totally fall out, you can see that the ejected flame is very big. I mean, suddenly, maybe 3 times bigger than the normal ejected flame. So I think suddenly, in maybe during only 1 or 3 seconds, but this is already very big threat for the fire spread. I think this is very interesting things. And, it also can, when the glass breaks and fall, it can also change the distribution of heat flux. So that means in the room, that means your structure will be subject to very different heating condition, before and after the glass fall out. So I think that's a very interesting thing. But for the full scale, like you said, last year we have conducted the 2 full scale experiments. One is there's no window and no door. We just burn the furniture, and the fire, just developed as a normal stage, the early stage, and the ventilate flash over and something. But it's only, it actually is only at the borderline to to make a flashover happen. But when after we finish the glass panel and the door, and during fire we close the window and close the door. Then we ignite the room. Something interesting happens, and the fire develops first, and then due to lack of the oxygen, the fire kind of self-extinguish. And also it may cause the direct bath if you open the door on the window. But so the room is with the temperature of more than 400 degrees for more than 10 minutes. So maybe there are some smoldering on the bed or on the sofa. And that what is interesting is that even the smoldering fire at last make the glass cracks and make the fail happen. So then after a while, then the fire become much bigger than the test one, after flashover. Yeah, so I think that's also very interesting phenomenon that it even make the fire bigger if you install the glass pan and if the glass fail out at some point.
For me, an interesting topic is the natural ventilation of offices, and we're doing a lot of research in that field. I'm not sure how it is used in China, but in Poland in particular, we see a lot of natural ventilation even in very tall buildings, because it gives many points in the green certificates, LEED, BREEAM. You get many points for having access to natural ventilation. And it's not that you have a whole panes of glass opened in the facade. No, it's more like you have these narrow panels, maybe 20 centimeters wide, which you can open, and they're like closed with a porous steel mesh outside. So you cannot even put your hand, but you can let some air inside. So I think even in such conditions, when you have some sort of ventilation for the compartment, like natural ventilation, it would be very difficult to oxygen starve the fire, like in your case, but it would still be not enough to develop into fully flashed over fire in a compartment. So it would be even closer to the conditions you've mentioned with the smolder. It would be some flaming combustion adding to the energy. So you could have this, let's say, pre-flash over temperatures for a very prolonged time in your compartment. And the second thing that comes to my mind, if you think about the traveling fire methodology that is commonly used now to design offices in large buildings, it preassumes that parts of your compartment are preheated by the fire that is far away. You have a fire that is far away, but the smoke is covering the whole compartment. So you still, even though the fire may be far away, you still have your glazing exposed to some high temperature from the smoke anyway before the fire comes. So these are two scenarios that come to my mind thinking about how pre-flash over fire can create damage to the glaze. And did you try to burn any objects directly against the window? Like, I don't know, an armchair, a sofa next to a glazing? Can a direct exposure to a fire to an item that is next to a window destroy that window?
You mean directly put the window?
Like if you have a window in your building and you put a sofa next to the window and you burn the sofa, so you consider the fire of that item, not the fire of the compartment. Will that be sufficient to destroy a tempered glazed window, or?
Okay, we do not burn this, but we do a profile, just beside the glass.
Okay.
Yeah, a similar condition. It's like the ambient condition.
Mm-hmm.
Yeah, it can make the float glass crack. Yeah, non-tempered, but it's kind of difficult to make the tempered glazing crack.
Especially if you have multi-layers.
Yeah, it has layers. Yeah, I think it's very difficult for in the open condition.
Understood. I also wonder if you reverse the problem when you discuss the separation between buildings or how fragile a building is to a wildland fire, for example. We often consider how easy it is for the fire to get into the compartment from outside. So I wonder also, like if you reverse the perspective, I guess because the windows are harder to break, they have better thermal properties, they have infrared reflective foils inside of them. They must be also much better in protecting the building from the fire that is outside or on a separate building. Have you had any experience with that?
So yes, when you put the fire inside the compartment, then it's a harass building fire or urban fire. But when you put the fire, why we did the fire, just make a pool fire just beside the window because we want to simulate the WI situation. Yeah, so I think the radiation is the primary way to make it break. And as I mentioned in the interview that I think also the frame material is also very important because you are subject to the firebrand issues. So if the window is closed, I do not think the firebrand may make the glass break, but it may ignite the PVC window frame or wood window frame. Yeah, especially I know as a fire, I know, but in China we do not use the wooden frame a lot, but in Europe and in America, especially in the WR areas, people like to use wooden frame. So I think this is very important to make sure that make the glass safety, to make the window safety. Yeah.
And in terms of the radiation being able to penetrate the glass, is it still like the outermost layer that would be the most exposed, or maybe some? Because you often use the shading foils inside of the compartment. We are not fully transparent to shade a bit or to reflect infrared radiation. And this would not be used, or is it used on the external? I'm not completely sure on the technology. Maybe it's used on the external layer of glass. But do you see a different, for example, temperature gradients inside the glazing in this scenario, or it's the same?
I think they are similar because the maximum temperature difference often occur just at the borderline between the covered areas, frame covered and the frame exposed areas. So no matter it's inside or outside, I think the maximum temperature difference is at that point. So the crack often initiates in the middle of the edge. It's often at the edge. So I think there are no big difference, between the inside and outside.
And a stupid question: if you have half of the window shaded, like if the radiation hits only half of the window and half is in the shade because you had a corner or something, will that create a temperature gradient that can also be more difficult for the glass to handle?
Yeah, I think this is a very clever question. If you change the shaded forms, it may change the crack location, I guess, because we also done some numerical simulation about this. We change different shade of this triangle, so that will be different. But the best is that when we change the installation or change the shade forms of the glazing, we found that if there's a hidden frame, no glass frame, then we do not make it break because there are no such big temperature difference when subject to a fire. You have no frame, for example, you are just hit the glass. The glass will not break. Yeah, so I think maybe this is some way to prevent the crack. I just imagine, because in Harvard buildings there are hidden frame. Hidden frame.
We see them a lot. Yes.
Yeah, but the problem is the glue. The structured glue between the glass and the metal areas.
And in the description of your previous experiment, you've mentioned the glass was exposed to approximately 400 degrees for like 10 minutes. That is a lot of temperature. Like in my school of engineering, how I was told, you could assume that the glass will fail at 300 degrees, maybe 250. You could see some cracks. I wonder, do you have numbers of what temperature to assume for this glazing to fail? Or it's too complicated and you need to go FEM modeling?
Yeah, actually for the engineering, I think you can assume it's critical condition for crack. And actually the factor for glass break is the temperature difference. Temperature gradient rather than the temperatures. So even though the room temperature is for maybe 500 degrees or 900 degrees, but you cannot say what temperature it is on the glazing and what temperature difference. So you have to measure the temperature difference on the glass surface so that you can determine, it may crack or not. So you can have to assume that. Yeah, I think the room temperature, glass crack in a very wide range of room temperatures because room temperature is not the critical factor for its break. Yeah.
And in your modeling, do you now have a way to couple this into the simulation? Because if I model my compartments in FDS, one way to do the glass breaking, you would set a device with a temperature trigger on it. And once this temperature is met, the glass would disappear and the wall would open. That is a common way we do this in CFD modeling. You think at this point it's a correct way or more sophisticated models are needed? And if so, Do you see these models be created and implemented in FDS in future?
Yes, I think because now while my students are doing the something you mentioned with the FDS, once the temperature reach some point or heat flux reach from it just remove the panel. Yes. It disappears. So yeah, it can simulate some environment phenomenon, but it's difficult for you to match the environment results. I mean, break time and the break time in the numerical simulation, very, very difficult. So I think FDS cannot predict very well for the glass breakage, but we need some more specific and some more complex modeling, I guess. So actually, you can also that is similar to the structure fire areas. You get the temperature distribution of the glazing, and then you do the FEM analysis in another solid software. Then you get the correct, the creep condition. Then it changes. So I think then it is very similar to structure fire.
It's interesting. Like if you have just the float glass or just a single layer of tempered glass, I mean, this approach you've mentioned or I've mentioned would be okay-ish to model that. If you have just one layer, but if you have multi-layer glass, especially with the air zones inside the glazing, so it makes a very and the PPV foil, it makes a very complicated thermal boundary condition inside. I mean, FDS has this 1D and 3D heat transfer models inside, so you could technically solve for that. But it could be interesting to have a glass boundary condition that you could put, and the software would know it's layers of glass that will break at this temperature gradient, and it could know that now 1, 2, 3 layers have failed, the fourth layer is exposed. Okay, now it broke completely, disappeared the element. That would be an interesting development. Maybe you guys, with developing your models, will be able to build something like that. Are you?
Yeah, this is what we are doing actually. I got a project from the start of this year, so we're focusing on these areas. So that's very interesting. Actually, we hope we don't want to make things very complicated. We want to understand the complicated issue and make these things very simple to be used. So we hope even in the current FDS, if we do some assumption or some simplification, that we still can kind of accurately, I mean, in an acceptable way, the predict the glass breakage. So I think that's also very cool because the computation time is also another factor we have to consider. If we make single glazing, so a lot of things I think that's not very efficient in the engineering. Yeah, so we want to make the things as simple as possible, but in an accurate way.
I also think the coupling outside and inside, like back and forth, would be difficult because so far I know it is fairly easy or very easy to extract from FDS to FEM models. I just had Thomas Journet on the podcast, and he was talking about Sapphire, how it does this extraction of the data, that there's already a model built in FDS to help that extraction. But if you extract to another software and then would like to come back to FDS with the information, now it broke and destroy the window, I think it is quite difficult at this point. Are you working with other numerical models as well besides FDS, or this would be development for, or it's just unrelated to software? It's just a third-party model outside of any CFD.
Yeah, because we have in-house software. For crack initially. So maybe we get this temperature, then we can really predict in our in-house software. Yeah. So, but this is still ongoing. So the students are trying and to compare the results with experiments. Yeah. So to modify, some numerical simulation often need a lot of assumption or a lot of time to be validated. Yeah. So we are doing this. Yeah.
Very, very good. Maybe just as a final question, how do you see the near future of glazing? Is there any new technologies emerging that will change everything in the next 10 years, like the tempered and laminated glass changed the last years, or we are now in a stable region and just slowly improving the technology? What the future holds?
Actually, I treated this area as a boundary condition of the fire dynamic problem. So we do not, focus too much on the glass technology. So we cannot predict what kind of new glass can appear.
Yeah.
Or maybe, yeah. But what we can predict is that the glass will be used as more often and more widely. Much more widely in the future, because I think it's similar to the people are like using the timber building, because timber make you feel very natural and very very nice. The glass as well. I can say in China, many buildings are using much more glazing, even the channel or the floors, and in maybe 5 years ago they like to use the concrete and steel, but people you like to use glass everywhere. So I think glass may be much more widely used in the future. I think this is more important than previous years. Yeah, so this is what we can see that.
And so sorry, I told you it will be 2 questions, but it's like now the question number 7. But it is so interesting. We also have these double skin facades, where you would have a facade of the building, then let's say 1-2 meter cavity, very large cavity, and like an external covering facade. I guess in this WUI scenario, it will also be very good, because you would have this frontal panel that can take the heat. And did you had an experience with this type of facades?
Yes, I think the problem for this kind of double skin is the smoke movement rather than the glass breakage. It's more about the flow dynamics. Yeah.
So the smoke entering the cavity between the facade and the second skin.
Yeah. So only it depends on where the fire happened. If the fire happened in the room, so after it breaks the window, so the smoke can directly go out. But I do not think it's very easy, to break the glass, in the upper floor. I think the problem is the smoke may go up and maybe enter the other.
As I said, you can have natural openings in Poland in these buildings. So you have a natural openings through which the smoke could re-enter the building, creating a very dangerous dynamics. This is actually something to consider with that should be a podcast episode. I'll note that down. I need to find a double skin facade expert now. That's so cool.
Yeah.
Okay. Yeah. And for the end, we have talked something about the future technologies. And one future technology that I see developing is different approaches to create energy generation within glass panels, like embed some sort of silicone foils or perovskite foils inside to generate electricity within the glazing. And I don't expect an answer, but I think this could be also a thing that changes the way how facades are built, used, and how they behave in fire. Do you have an opinion on these new technologies?
You mean the PV panel?
Yeah, but even like PV panels, when you put them on a facade, that's one topic. And I see that happening. I know there was like one building in China which had like the whole facade of the building covered with PV, and that was amazing. It was an insane generation of energy. But I read in like pop science magazines that they would like to embed the PV inside the glass, like a foil inside the so it would be a part of the glazing. You would probably not even see the foil being in there. So you could cover the whole building with this type of foils and panels.
Yeah. Actually, this is the new research direction in my group as well. So I think the substantial issue is a glass breakage issue. Actually, what you mentioned is similar to laminated glazing, right?
It's similar. Okay, so similar challenges. I also wonder how we will handle all the cables inside the facade structure, especially if it's PVC. I see a risk with the cables and energy transport and firefighting operations on facades that are under electricity. So that is a whole array of challenges emerging.
It's much more complex.
It's much more complex. Okay, this was very insightful. I look forward for the work of USTC in the field of facades and every other field that you're researching. I know your group at your laboratory is like one of the biggest, if not the biggest, in the fire science. So I'm really happy that the Fire Science Show finally came to China and had the guest from the biggest group out there. Congratulations on what you are doing and all the best for the future. 谢谢.
Oh, thank you, Vijay. Thank you for the invitation, and thank you for the audience for listening. Yeah, I will show I think this is very good show. I will show it to the colleagues and the class, the students in our state key fire lecture.
And that's it. Thank you for listening, and thank you for coming to the Fire Science Show and telling all of us all about the glazing in fire. It was certainly a very interesting and packed with information episode. I could not extract a single number from you on what temperature the fire will break the glass. I guess we have to stick to the literature reviews, and you has written some great papers. I'll cite them in the episode show notes so you can unravel. I really enjoyed talking to him. I really enjoyed the research they are doing and developments they're doing at the USTC, especially the ones related to creating new models. If we could get a glass breakage model that we could implement somehow into FDS or other CFD codes that are being used, and just have a glass boundary condition, and just have the software figure out at what point the glass will break, crack, fall off, and to what extent that fall off will be, we would enter a whole new level of modeling. Today, we're doing that in a very simple manner by creating devices, opening parts of the model as soon as certain temperatures are reached. I mean, it works. It's better than nothing, but I think thanks to models like the ones created by EU Steam, we can really up this game and really improve our modeling skills and make these simulations more realistic. And if we couple that with models that use real fuels, they use ignition, solid phase, pyrolysis, combustion. They just model the fire, actually. If you couple that with a really good model for ventilation conditions, we are closer and closer to modeling real compartment fires in our CFD, and that's a beautiful direction. And as soon as I see something emerging in the field that brings us closer to this solution and that helps us understand real fires better, you may be sure I'll bring it into the podcast. And that would be it for today's episode. I also hope it will let me reach some new listeners in China. I really hope for that. You has promised me to share this episode with their internal mainland channels and help to spread the word about the podcast. So I really hope to find new listenership in China, where I did not have that money. And that would be great news for the podcast, reaching more engineers and more scientists around the world. And also, as usual, if you know an engineer, if you know a fire scientist, you know a firefighter, or anyone else who could benefit from listening to the Fire Science Show, please let them know that the show exists. Yeah, and thank you for listening. See you here next week, next Wednesday. Cheers. This was the Fire Science Show. Thank you for listening, and see you soon. And see you soon. And see you soon. And see you soon.